Okay, so real quick, the thing we looked at yesterday, right? We were talking about how you could do this u substitution with a definite integral, and it gave you the bonus of not having to reverse the substitution. Okay, let's just look at this graphically. It's pretty amazing. So if we do something like, for example, we had this original integral, which is nothing too crazy, right? Let's graph that. Let's graph what this area looks like. So I've got this little setup here where I can put in a function and it'll calculate the area under the curve, but it'll show us it'll represent the area graphically. So we got x times the quantity x squared plus 1 quantity squared. And we want to go from, what, 0 to 1. Okay, so 0 to 1. And so that's our area, right? And we end up getting, looks like, what is that, 1 1/6, so 7/6. Is that what we got? Hopefully, yeah, 7/6. Okay. Right, so there it is. Oh, wrong one. That's my other class. And it's that one. Okay? So there's what our area looks like. Let's make that look a little better, and we'll take a picture. $2.5, yeah. Okay, so there's our picture. I'll just record this for posterity for you. So there's the area that goes with that function. Right? Okay, now let's find the area that goes with that function. This is so fun to just play with my toys. All right, so now we're just doing u squared. So I'll change my function. I'm going to call it x squared instead of u squared. But we're just going to do x squared. Oops, I had it right there. X squared times 1/2, right? And we're going to go from 1 to 2. Because that's what we made when we made our u substitution. Remember that when x was 0, u equaled 1, and when x was 1, u equaled 2, right? Okay. So what do you know? We get the same area, right? But the curve looks very different, right? This just looks like a quadratic. That last curve looked like some bizarre cubic, right? Oh man, come on. There's what it looks like. Right? Totally different looking shapes, but the math gods in their wisdom give us the same areas. Right? It's just easier to add up the area under that curve than it is to add up the area under that curve. Right? So there's you sense we have this theme going on. In math, we do this a lot. Sometimes we'll trade one problem for a completely different kind of problem as long as they have the same answer. Right? We'll shift into a different space in order to solve this thing. This is in X space and this is in U space. Right? But we don't have to shift back this time because all we want is the area. Right? Okay. Let's do one trig one like this, and then I think you can just work on this stuff. You gotta get some practice. All right, so how about if we do something like, of course they don't really have any good ones there. Let's make one up. Thank you. Oh, you're fine. Yeah. Okay, let's try that one. So what's our U substitution going to be this time? Sin x. Okay, good. So if we let U equal sin x, what's du?
Just cosine x.
Cosine x dx. Okay, so we have a clean substitution then, don't we? Right? So we end up with this is equal to the integral of, what's that going to be? U to the 1/2 du. Okay, but what are my limits going to be this time? So when x is 0, that's going to become u equals what? 0. Sine is 0, right? Okay, what about when x equals pi? What's u equal to? So this, we have an advantage here, don't we? So this is going from 0 to 0. What's the answer? 0. Yeah, I don't even have to do any calculus, do I? Right? I mean, it's not hard calculus to do, but what if it was? Right? What if this was a really tough integrand? Making this substitution just by our property of definite integrals that says if the upper and lower limits are equal, there's no area, right? Because there's no width to the area, right? Let's just look and see what we know what that area is going to look like. It's not going to look like anything. What do you think the top area is going to look like? How is it going to come up with a 0 answer? There's going to have to be some positive and some negative, right? So let's try this. So our function is square root sine x. Well, we got to make sure I'm in the right mode too. So I've got to be in radians mode. Where do I do that? Probably up here. Yeah, I'm in radians. Good. square root of sine x times cosine x. And if I go from 0 to pi, what do you know? What do we find? Got symmetric lobes on the graph, right? So you can see that makes sense. That does go to 0, doesn't it? Right? Okay? Make sense? And obviously, I mean, do we even need to graph that one? It's just it doesn't matter what the curve looks like. It's got no width to it, right? Okay. All right. That makes sense? We'll do more of these, but I'm just going to let you get started. I'll let you do a little work. Okay, and we'll come back, and I'm sure you'll have questions, and we can go through some more of these. But you can at least get some of the starting ones done.